Hi everybody, in this video we continue with Chapter 4, Geometry and Trigonometry 1, specifically Section 4.3, Non-Right-Angled Trigonometry. So the first thing we're going to do is look at this figure over here, and you will notice that there's an angle theta. This is an angle theta. Now this angle is obviously in a Cartesian plane. As you can see, there's an x-axis and a y-axis. But basically what you have to pay attention to in this example or in this figure is the fact that angles, when they are positive, they are measured counterclockwise. So that means from right to left. And notice that each quadrant is also denoted here. This is quadrant 1, this is quadrant 2, quadrant 3, and quadrant 4. It denotes the 4 parts in which the Cartesian plane can be divided. And also notice that they are counted from right to left. In other words, counterclockwise. This red thing here, this red line, is what's known as the terminal arm. That means where the angle ends. Now, since we measure the angles from right to left or counterclockwise, this would be 0 degrees here, right at the x-axis. And if we have an angle that reaches the y-axis from this point here, this would be 90 degrees. This is 180 degrees. This would be 270 degrees. And if we go all the way around back to 0, this would measure 360 degrees. So what I mean is 90 degrees up to here, then 180 degrees up to there, then 270 degrees up to here, and 360 degrees would be a full circle. So bearing all this in mind is how we're going to solve the next example. So here we are with example 4.15, and it says by drawing an appropriate triangle, calculate the following, right? So letter A, sine of 120 degrees. So what you do here is you use the Cartesian plane as a reference, and then you know that up to here it's 90 degrees, 30 degrees more, so it would be more or less here. So this is your terminal arm right there, and let's say this is 120 degrees. Now in these cases what you're always going to do is that you're going to use the x-axis as your reference. So how many degrees are left till we reach 180, which is the x-axis on this left-hand side? So remember, this is the x-axis and this is the y-axis. So how many degrees are left? So if we have 120, we still have 60 more degrees to go. So 60 degrees right here, 60, is going to be our reference angle. So we draw a triangle, and that's going to be our reference triangle. Since this is 60 degrees, remember that this here, this other vertex would have 30 degrees. So this is 30 degrees, 60 degrees, and 90. Does this look familiar? Well, yes, this would be a special right triangle, right? The 30-60. The 30-60 would be our reference triangle. So we know that this is 60 and this is 30. And previously we learned that the 30-60 has a ratio that is always the same for all of these triangles, right? Remember that it's going to be 1 opposite the 30. Then it's going to be 2 for the hypotenuse, and square root of 3 opposite the 60 degrees. Now, in this case, it's going to be a little bit different. This measurement here is -1. So let's use -1 here. Now, since they want us to find sine, this negative is not going to affect anything, because sine of 60, we know, is square root of 3 over 2. So that means then that sine of 120 is going to be square root of 3 over 2. So that's the solution to this one. Now for B, they want us to find the cosine of 135 degrees. So we proceed in the same manner. We draw the Cartesian plane, we draw a terminal arm, which would be right here. Notice that this is 90 degrees, and then we need 45 more to get to 135. So this is 135 degrees, which is what we want to find the cosine of. So how many degrees are left? 45. 45 degrees. So our reference triangle is going to be the 45-45 one. And remember that this is the x-axis and this is the y-axis. So what does our reference triangle look like? If it's the 45, 45, if this is 45 degrees and this is 45 degrees, remember it's going to be 1, 1, and square root of 2. Now we also have to take into account the signs of these numbers. Notice that here y is positive, right? Y is positive. We have negative for x, positive for y. Here both are positive. In this other case, here they are both negative, right? X is negative, y is negative. And in the fourth quadrant, we would have that x is positive and y is negative. So in other words, what does that mean? Well, x is negative in this quadrant, right? This is the second quadrant. X is negative. So we need to use a negative one. Now, that means that cosine of 135 degrees is going to be negative 1 over the square root of 2. Now you can verify these results with your calculator. So now let's focus on C and D. For C, they want us to find the tangent of 210 degrees. Okay, so we use a Cartesian plane, x-axis, y-axis. And then where is 210 degrees? Now notice that all the way to here is 180. So how much more are we missing to get to 210? 30 degrees more. But we always use the x-axis as the reference. So this triangle would be backwards. Now I'm going to draw it over here just to be a little more comfortable. So this one would be like this. So this is the right angle over here. And our reference angle is this one, right? With the references with respect to the x-axis. So this is going to be 30 degrees. So this is a 30-60. 1, 2, and square root of 3 opposite to 60 degrees. But notice that everything is going to be negative except the hypotenuse. So notice that the x-axis is negative here. The values on x are negative, so this is negative. The y values are negative because it's below the y-axis, so this is negative. So tangent, recall that tangent is equal to opposite, a tangent of an angle, I should say. Tangent of an angle theta is opposite over adjacent, right? So in this case, you would say tangent of 210 degrees is equal to opposite, so opposite the 30, right? Which is our reference angle, minus 1 over the adjacent, which is negative square root of 3. So minus 1 over minus square root of 3. And this is going to give us positive 1 over square root of 3. Now for D, they want us to find sine of 315 degrees. So notice that 315 degrees is going to be almost a full circle. So this is x, this is y. The angle they want us to find, or the sine of the angle they want us to find, is 315 degrees. So it goes something like this. And this would be the terminal side. Now, excuse my drawings. The reference angle is this one. So how many degrees, I should say, are left to reach the 360? So notice that we would need 5 for 320 and 40 more. So that means 45 degrees. So let's draw it over here. So we have, it looks more or less like this, right? So this would be the right angle. And then this is 45 and 45. And this, of course, right. Now, normally it's 1, 1, and square root of 2. So let's look at what's positive and what's negative. So what is positive? Well, we have that the x-axis is positive at this point here. The y-axis is negative, so this should be negative. And the hypotenuse is always going to be positive. So sine of 315 is then going to be equal opposite. So this is our reference angle here, right? So this one over here, opposite, minus 1 over the hypotenuse, square root of 2. So this would be the answer for D. So next we're going to take a look at example 4.16. And part A says, show that for any angle theta that is between 0 and 90 degrees, sine of theta is equal to sine of 180 minus theta. So we can prove that or show that using this illustration here. Now, notice that this angle here, if this is theta, right over here, if this is theta, then 180 minus theta would be all this. This would be 180 minus theta. And this theta here is our reference angle. So take a look at a couple things here. First of all, notice that this is the y-axis. And if we take this as a reference here, this A is going to be positive, like this one over here. And C, the hypotenuse, is always going to be positive. Now, what would be different would be, let's say, call this B. If this is B, this would be negative B. But this does not affect sine, because notice that for this triangle over here, sine of theta is equal to A over C. But we have the same situation here. Notice that this reference angle here, theta, so if we do sine of theta, this is also going to equal A over C. But this is our reference angle. Notice that this would be the same as saying that sine of 180 minus theta is equal to A over C. So in other words, we have the situation that for any angle between 0 and 90 degrees, we have the equality that sine of theta is equal to sine of 180 minus theta. So this is a very useful equality, as we're going to see. Now for part B, it says find two different angles theta with sine of theta is equal to 0.65. So they're not giving us the angle, we have to find the angle theta. So notice that theta is equal to the inverse sine of 0.65. If you plug that into the calculator, it's going to give you approximately 40.5 degrees, and this is rounded to 3 significant figures. So what would be another angle theta that would be equal to this? Well, it would be 180 minus 40.5, and this is going to give us 139.5 degrees. So what that means is that sine of 40.5 degrees is equal to sine of 139.5 degrees. Then for part C, they say, show that in a triangle containing an obtuse interior angle theta and two enclosing sides with lengths A and B, the area is given by the formula 1/2 AB sine of theta. So obtuse means more than 90, right? So that would be something like this. Let's say it's like this. So this is theta. And let me try to draw this side here. Okay, so enclosed by sides with lengths A and B. So let's call this A, and let's call this side here B. So notice that if we do something, if we draw a height, say from here, let's draw a height, and we draw a right angle, notice that, let's call this H. Notice that we can use this as a reference, right? This angle here. Now, the thing is that this angle is equal to 180 degrees minus theta, right? Why? Well, because all of this is 180. So if this is theta, this part here, if this is theta, then this other part here is 180 minus theta. H, the height, I'm going to write over here, H, the height, is going to equal B times the sine of 180 minus theta. Why? Well, let's do it differently. Well, notice that if I want to find the sine of 180 minus theta, sine of 180 minus theta, in other words, the sine of this angle here, is going to be opposite h divided by the hypotenuse, which in this case would be b. So h over b. So if I send this to multiply, I'm going to get this expression, right? H is equal to b times sine of 180 minus theta. But we already said that sine of 180 minus theta is the same as sine of theta. So that means that we can express the height as being b times sine of theta. Now we know that for any triangle, the area is 1/2 times the base times the height. So that means that for this triangle, the area is going to be 1/2 times the base. The base here is A, so 1/2 times A times the height, which we said is this, b sine of theta. So there you are. So next we're going to take a look at something called the sine rule, which is a very useful rule for solving problems with triangles that are non-right angled triangles. So it says the ratio of a side length of a triangle to the sine of the interior opposite angle of the triangle is constant. This is called the sine rule. So in any triangle with side lengths ABC and opposite interior angles capitalized ABC, this relationship holds true. A divided by the sine of angle A. So that means that this A here, this side A divided by the sine of this angle A is equal to side B divided by the opposite angle, sine of B, is equal to C, side C, divided by the sine of the opposite angle C. And then also the reciprocal is true, which is this. In other words, sine of angle A over side A is equal to sine of angle B over side B, and that is equal to sine of angle C over side C. So now let's do example 4.17. Find the value of the missing side length x in the triangle shown in figure 4.27, correct to 2 decimal places. So this is a typical case where we would apply the sine rule. Notice that x divided by sine of 25, right, the opposite angle, is equal to 14 divided by sine of 65. Now, what I always recommend to do is just plug the whole thing in the calculator. Notice that x is going to equal 14 divided by sine of 65 times sine of 25. So plug this whole expression, and you're going to get an answer that is approximately 6.53 rounded to 2 decimal places, and don't forget the units, centimeters. So we continue with example 4.18, and it says, find the missing value of theta in the triangle shown in figure 4.28. So they want us to find theta. Now, in this case, we're going to use the reciprocal of the one we used before. So let's say sine of theta over 10 is equal to sine of 60 over 9. So that means that sine of theta is equal to sine of 60 over 9 times 10. Now don't multiply 60 times 10, right? This is two separate operations. But they want the angle, so we have to use the inverse sign. So we say theta is equal to the inverse sine and plug in the whole expression. Sine of 60 divided by 9 times 10, and this is going to give you approximately 74.2 degrees rounded to 3 significant figures. So now we're going to take a look at the cosine rule. And the cosine rule says in a triangle in which two side lengths A and B, as well as the enclosed interior angle theta are known, the side C opposite to theta is given by C squared is equal to A squared plus B squared minus 2 times A times B times cosine of theta. So that means that we can find this side if we have this side, and the angle that is enclosed by them using this formula. Now, notice that we can rearrange the formula. So this would allow us to find cosine of theta. And also we can find theta by using the inverse cosine of this expression. So now we're going to go and do some examples to apply this. So let's now focus on example 4.19. And it says, find the value of the missing side length x correct to 2 decimal places. So for part A, we would just have to apply the cosine rule, right? We would say x squared is equal to 4 squared plus 5 squared minus 2 times 4 times 5 times the cosine of 30 degrees. So this means that x is equal to the square root of this expression. So 4 squared plus 5 squared minus 2 times 4 times 5 times cosine of 30. We plug this into the calculator, and it's going to give us approximately 2.52 centimeters. Don't forget the units. And they said rounded to 2 decimal places. So for B, we proceed in a very similar way, right? We would say x squared is equal to 6 squared plus the square root of 17 squared minus 2 times 6 times the square root of 17 times cosine of 150. So that means that x is going to be the square root of all this, right? X is going to be the square root of this, and this is going to give us approximately 9.79 centimeters rounded to 2 decimal places. So next we have example 4.20, and it says, in each of these triangles, find the angle theta to the nearest degree. Okay, so remember that the formula for calculating an angle using the cosine rule would be that theta is equal to the inverse cosine of a squared plus b squared minus c squared divided by 2 times a times b. So what is a, what is b, and what is c? Remember that a and b are the sides that enclose the angle. So this would be side A, this would be side B, and this is side C. So that means that in this case A, so for A, theta is going to equal the inverse cosine of 7 squared plus 11 squared minus 10 squared divided by 2 times 7 times 11. Plug the whole expression into the calculator, and then we have to round it to the nearest degree. So this is approximately 64 degrees. So for B, let's say this is A, this is B, and this is C. So that means that theta would be inverse cosine of, let's say 16 squared plus 21 squared minus 27 squared divided by 2 times 16 times 21. Plug the whole expression into the calculator, and it's approximately 93 degrees rounded to the nearest degree. So next we're going to work on example 4.22, which is the last one on this video. And it says, an aeroplane flies 280 kilometers on a bearing of 9 degrees from Calgary, Alberta, in Canada, to the provincial capital Edmonton. From Edmonton, the plane flies 1,320 kilometers on a bearing of 72 degrees to Churchill, Manitoba, located on the shores of the Hudson Bay. Part A, how far is Churchill from Calgary? So notice that we have a diagram here to the right, and they want us to find this distance here, D, from Calgary to Churchill. So remember that bearings are always measured from the true north. So a bearing of 9 degrees from Calgary to Edmonton is represented in this graph by this here. This is the angle of 9 degrees. The plane flies 280 kilometers, reaches Edmonton, and then from Edmonton flies 1,320 kilometers to Churchill, Manitoba on a bearing of 72 degrees. So again, from true north, we measure 72 degrees. Now, obviously, we want to apply one of the rules that we learned. Now, the most convenient one would be the cosine rule. But for that, we need the angle opposite D, right? That means that we need to know the measurement of this entire angle. So we can do a trick with this. What we do is that we grab Edmonton as a vertex and we draw a 90-degree angle, like this one here, you see, 90-degree angle. And then there's a couple of things that we would know. First of all, that there would be 90 degrees here as well. But since we have 72, it means that we're missing 18 degrees to reach this line. So that means that this little piece of this angle measures 18 degrees. Then we know that this is 90 degrees. And then we also know that this little bit that is missing here is 9 degrees. Now, why is that 9 degrees? Because if you have two lines that are parallel, like this, and then you have a line that crosses those parallel lines, like this, you have the case of alternate interior angles. So notice that this angle here, is equal to this angle here. So that's the principle we are using. So now we know that this entire angle here is going to be 18 degrees plus 90 degrees plus 9 degrees. And this equals 117 degrees. So we're ready for part A, because using the cosine rule, we know that d squared is equal to 280 squared plus 1,320 squared minus 2 times 280 times 1320 times cosine of 117. So we square root all this. Now plug the whole expression into the calculator to avoid mistakes. And we have that D is going to be approximately 1,468 kilometers. Then for part B, it says, if an aeroplane flies at an average speed of 720 kilometers per hour, how long is a direct flight from Calgary to Churchill to the nearest hour? So they want us to find time. Now remember from physics that time is equal to distance divided by speed. So in this case, the distance is 1,468 kilometers and the speed is 720. And if you plug that into the calculator, it's approximately 2 hours.